Hello, welcome back to another episode of Math with Haas. You are watching Precalculus Season 1, Episode 14. We are continuing our investigation of exponentials and logarithms. In the last three episodes, we looked at applications of exponentials, and in particular, we looked at the growth models, doubling time and relative growth rate. We looked at radioactive decay and Newton's law of cooling. Now we are going to begin looking at applications of logarithms, and our first two examples come from chemistry and physics. So I'm sure you've heard of chemistry, like acids and bases, and how pH is used to measure how acidic a solution is. Well, pH is going to equal negative log, and then funny bracket H plus and funny bracket. So this is the equation for pH. This will measure how acidic or basic a solution is. So let's talk about our equation for a moment. So when we see this H with a plus, that means ionized hydrogen. I misspelled hydrogen. Awkward. Hydrogen. So the hydrogen atom is said to be ionized when it has a positive charge here. So when I look at this plus sign, that tells me it's ionized. In fact, it also tells me that it has a +1 charge. So this formula for pH has something to do with ionized hydrogen. And in fact, these square brackets have a particular meaning as the molarity of ionized hydrogen. Alright, so molarity, if we want to put it in layman terms, we could think of it as concentration. Okay, so think of this as the concentration of ionized hydrogen in a solution. So if you know what the concentration is, what the pH will be is you take the negative of the log of your concentration, and I'll tell you the pH. So if your pH is less than 7, your solution is said to be acidic, and if your pH is equal to 7, then it's neutral. And a pH greater than 7 is said to be basic. So what makes a solution acidic is that it has a large concentration of hydrogen ions, and what makes a solution basic is if it has a high concentration of these hydrogen monoxide. I forget. Yeah, hydrogen monoxide. Hydrogen monoxide compound atom molecules. You can tell I'm not a chemist. Anyways, when you have a higher concentration of ionized hydrogen than you do OHs, then your solution will be acidic, but when the concentration of these OHs is greater than the ionized hydrogen, then your solution is going to be basic. Okay? And when we think about water, water is said to be neutral, because if you think of H2O, you could think of it as a hydrogen plus one of these O's. That get it? OH. O. Alright. I'm sure I made some chemists cringe. Alright, so talking about this, let's see. So we've talked about the equation, we talked about what's going on, we talked about why water is neutral. Now we need to look at doing some math with this, with our new bestie here. So if you were told that some solution had a molarity or a concentration equal to about 3.8 times 10 to negative 7, the units for this for measuring concentrations denoted with the M for molar. Alright, so if this is our concentration, then our pH is going to equal negative log of this quantity. Alright, so we go negative log 3.8 times 10 to the negative 7, and voila. So this solution will have a pH of 6.4. Now, if you were told that the pH of some solution was, say, 2.7, and you want to know what did the concentration of hydrogen ions, what was that concentration, we can set it up like so. So we have 2.7 is equal to negative log of our molarity of hydrogen. And now we have a nice simple logarithm equation that we can solve. So first I'm going to isolate the logarithm by multiplying both sides by -1. So I have negative 2.7 is equal to log of our molarity. And then now I want to exponentiate both sides with log base 10, or not log base, we want to exponentiate both sides with the exponential base 10 because we have the common logarithm, which is base 10. So we get 10 to the negative 2.7 is equal to 10 to the log of our molarity of hydrogen ions. And then we want to recall the fact that if you have a to the log base a of x, this is going to equal x. So by our property, these smote each other upon the mountainside, leaving you with 10 to the negative 2.7 equaling our concentration of hydrogen ions. And 10 to the negative 2.7 is going to be almost 2. So we'll just round this to 2. So 2.0 times 10 to the negative 3 molar. That's our concentration. Alright, so that is our first example of using the logarithms. A second usage for logarithms is, as I mentioned before, physics, and it is the decibel scale. So the decibel scale measures how loud a sound is. Okay. And since we're measuring how loud a sound is, we want to think of comparing it in terms of the human threshold of hearing. So the human threshold of hearing, the lowest that we can hear, is going to equal it's about 10 to the negative 12 watts per meter squared, which is very quiet. Now this quantity I'm going to denote with a I naught. Okay. So our equation is going to be the following. How about we use a D for decibel? So D is going to equal 10 log of I over I naught. So what is happening here is you have a intensity I being divided by our reference intensity, which is the human threshold for hearing, this 10 to the negative 12. And by using this ratio, this gives us a comparison as to how loud our observed sound is. Now, these values can be really big or really small. 10 to the negative 12 is quite a small number. And that is the power of logarithms. Logarithms allows us to take really small numbers, like 10 to the negative 12, this 10 to the negative 3, and turn them into more manageable numbers. Like, so we go back to our pH here. This 2.7 is a lot more manageable than a 2 times 10 to negative 3. And similar with this pH of 6.4 versus 3.8 times 10 to negative 7. We'll have a similar experience here. So, one thing to note is by selecting our I naught to be this value, if you have, say, if you want to figure out what is the loudness of the human threshold of hearing, if you were to plug that in, you get 10 log of 1, which we know is just going to be 0. Log, doesn't matter what base of log is, log of 1 is 0. And it should make sense that this is 0, right? Since this is our threshold for how loud a sound is. So that's one interesting note about our equation. Another interesting note is D, which is our decibels. That's measured in the units dB for decibel. So deci is from the metric system. So you think millimeter, there's centimeter, and before that there is a decimeter. So deci is like 0.1 meter, or yeah, it's 0.1 from the from whatever your unit is, whether it's meters, grams, liters. Whereas centimeter would be like 0.001. No, just 0.01. I got carried with my zeros. And then this bell, that is our unit for sound, and that comes from, well, let's say it's named after Alexander Graham Bell, who was the inventor of the telephone. That's what this decibel thing is getting at. That's the historical note and metric note of the origins of it. So our equation, our decibels are equal to 10 times log of our observed intensity of some sound divided by the human threshold of hearing, I naught. So let's go ahead and do a example or two. Ooh, got I said blue on. Alright, so suppose, actually, we should probably use some actual values. Let's see here. So, heavy traffic has a decibel value of about 85. So heavy traffic has a loudness of about 85 decibels. So what does the intensity equal? So 85, that's our D, is equal to 10 log of I over I naught. So I is the unknown we're looking for. We are told that we already know what I naught is. That does not change at all. That will remain 10 to the negative 12 regardless. So to solve this, we can note that we have a logarithm equation that we need to solve. And our first step is to isolate the logarithm. In this case, we have this 10 in front that we need to get rid of. So I'm going to divide both sides by 10. So I have 8.5 is equal to log of I over I naught. Now, since our logarithm is the common log, I'm going to exponentiate with our exponential base 10. So we have 10 to the 8.5 is equal to 10 to the log of I over I naught. And again, these two will slay each other, leaving us with 10 to the 8.5 is equal to I over I naught. Now we just need to multiply both sides by I naught. So we have I naught times 10 to the 8.5 is equal to I. And since I naught is 10 to the negative 12, we have 10 to the negative 12 times 10 to the 8.5 equaling I naught. And we can now figure out what that is. And that's the same thing as 10 to the negative 3.5. Alright. So let's figure out what 10 to the negative 3.5 is. That's convenient. Put in scientific notation for us. So I is equal to let's say 3.16 times 10 to negative 4. This is watts per meter squared. So intensity is always in these units here. Okay. So that's an example of heavy traffic and how intense it would be. Alright. Well, at this point, we're gonna call this a day for this video. We have another example of applications of logarithms, and that has to do with the Richter scale and measuring the magnitudes of earthquakes, and that we should dedicate its own video to. So thank you for watching this video of Math with Haas. If you've been enjoying our content, please subscribe and consider supporting us on Patreon. Thank you for joining our math party, and I will see you next time.